Hello everyone, my name is Milana and I am a PhD candidate at University of Nevada, Reno. So my focus is design and detailing of axial UHPC columns, and with Professor Mustafa, we designed, constructed, and tested 22 9-foot tall UHPC columns. Today I'm going to talk about the confinement effect of spirals and hoops on axial behavior of UHPC circular columns. Nothing would be possible without our donors. So Confab did an amazing job, Core Tough, then ABC UTC, and then PCI West. Ruth Lehman was amazing support to us. So outline of my presentation, I will start with introduction, motivation, and objectives, and then I will talk about experimental program, my favorite part, and then I will talk about the results and discussions, and then I will close this presentation with concluding remarks. So, as we all know, UHPC has amazing properties, basically superior mechanical properties when compared to normal strength concrete. However, especially on the structural level, it's underutilized. Major applications are for accelerated bridge construction joints, road and bridge repairs and rehabilitation. And the minor ones are for bridge girders, building components, then architectural features, or maybe in energy sector. So motivation, like we were just talking, so it's rapidly growing market. There are more and more vendors with many types of UHPC economical, ones that are actually becoming more and more popular. So basically increased number of projects, but in general there is a lack of comprehensive knowledge on economical UHPC. Basically when I say economical, that means that sand and cement are locally sourced. Also, we want to take the bridge structures to the next level, right, using UHPC. And in general, the knowledge gap is on the confinement effect provided by spirals and hoops, basically when we compare the spirals versus the hoops in the axial columns. So specific objectives of this study, basically it's to understand structural axial behavior of economic fully precast UHPC columns, then to demonstrate large-scale production using the precast UHPC columns, then to understand the effect of transverse reinforcement when we are talking about spirals and hoops in circular columns. And then from there to assess the design, ACI design equation, see how much they are actually conservative. Like, you know, do we have to correct any strength reduction factors when we are talking about the spirals and hoops? So for this research, so today I'm going to talk about only 4 columns. So they're, again, 9-foot tall columns. They are 16-inch in diameter. You can see that we had 2 of them spirally reinforced, and then 2 of them had hoop reinforcement. So basically, we varied the spacing. For spirals, we had one column that actually had 1.5 inch of spacing, and then we had another one that had 3 inch of spacing. Same thing actually applies to the hoops, so 1.5 inch spacing and then 3 inch spacing. All of them had 10^6 longitudinal rebars. Yeah, I just wanted to explain this. So you can see instrumentation plan, we used more than 20 strain gauges. So basically what we did is we implemented the strain gauges on the rebar surface for longitudinal rebars and for transverse reinforcement rebars. So for longitudinal ones, we had 4 different layers that you can see basically throughout the height of the column. On 3 different, out of 10, on 3 different longitudinal bars. So we just wanted to see the behavior of longitudinal rebars. The same thing we wanted to do for transverse reinforcement, where we had 14 strain gauges. They were distributed on the 7 different locations. What we did is that we put 2 strain gauges on the same level, but on the opposite sides. We wanted to just see what load my strain gauge is actually seeing on opposite sides. We did specifically because in the previous columns we observed some eccentricity effect just because of this data points that we got through the strain gauges. So ingredients of UHPC mixer. So like I mentioned, so we are using the economic UHPC. Basically, we are using the locally sourced sand and cement. Besides that, we are using, of course, water, and then steel fibers in, it was 2% by volume. And also we used admixtures. There were 3 types of admixtures. So one was corrosion inhibitor, then one was actually just to help with the workability, and one to reduce needed water. Mixing procedure. So we actually were using a large-scale procedure. So we were using the pan mixer and together with a rotational truck mixer. So how actually it went? It went that we put all the dry mix, all the dry components, right, with water into the pan mixer. Mix it for about 20 minutes, then transfer it to the truck. Truck drove like a little, like couple of feet away, and then we added all the admixtures. And then at the end, like Professor Mustafa mentioned, we were adding steel fibers manually, basically. And then the truck basically moved, came to the rebar cages that were in the sonotubes and poured all of the concrete into the cups, the formwork. Besides columns, we had more than 20 3x6-inch cylinders. We just wanted to test them and see during the time, right, how our strength is propagating, which is simulating the basically propagation of the strength in columns. Also, the columns were steam cured for first 48 hours, and then after that, we just covered them with the heat blanket. So test up and instrumentation. So we had 6 LVDTs. So we had 2 of them that had 7 feet of gauge length, and then 4 of them with 5 feet. Also, we had string pods that were just measuring throughout the whole height of the column. We wanted to capture as best as we can the compressive, basically deformation of the columns. We were testing all of the columns at the UC Berkeley peer lab under the testing loading machine with the capacity about 4,000 kips. So the next one. So mode of failure. So our concrete field. By visually we actually observed that some of our rebars buckled. Also, we couldn't see any cracks, any crack propagation, or hear any sounds up to 80% of the failure load. The failure was suddenly occurred, and it was followed by the loud sound. It's very important to mention that none of the concrete actually got detached. So it stayed, and this is basically the consequence of using the steel fibers that were bridging the micro cracks and basically preventing any spalling of the cover concrete. So summary of key test results. So basically in terms of the axial load capacity, the spirally reinforced columns with 1.5 inch of spacing and columns with hoops with 1.5 inch spacing performed pretty similarly. However, the column with spirals with 3 inch spacing had about 8% higher axial load capacity than column with hoops with 3 inch spacing. So when we are talking about the force strain graphs, so basically, again, the spirally reinforced column with 1.5 inch definitely performed the best, together with a column with hoops with 1.5 inch of spacing. And with the previous conclusion that the basically axial load capacity of the columns with smaller spacing, it's very similar to the conclusion with for the strain capacity. Basically, it's directly proportional to the percentage of transverse reinforcement used. So local behavior. So with these strain gauges, we could actually observe that all of our longitudinal reinforcement yielded approximately at the same time. With this strain, we could see that there was no any of the eccentricity effect. Because if there was, we would have some deviation between the curves at the beginning. Right at the beginning, it would be so obvious. Definitely no eccentricity effect, and we didn't have to account for it. For the transverse rebar strain, none of the instrumented transverse rebar yielded. That means that the failure, basically the buckling happened locally, and these instrumented transverse strain gauges, right, on the transverse reinforcement rebars didn't catch it. So that means that basically our confinement was not fully engaged, just because of this not yielding. So safety margins, when I say safety margins, basically I think about the factor of safety, which was the ratio between the basically axial load capacity, P maximum, that we recorded during the testing, and then the value that we got using the ACI design capacity value. As you can see, for the hoops with 1.5 inch of spacing, you see the number of 2.1, which basically means that maybe the design is a little bit too conservative. So to put that number down, right, maybe we should think about another strength reduction factor when we are using the hoops closely spaced. So instead of using a 0.65 for hoops when they're closely spaced, maybe we should actually just replace that number by 0.75, the same number that we are using for the spiral reinforcement. And then concluding remarks, overall, the large-scale production was successful. We designed, constructed, and built large-scale columns using the precast plan. For 3-inch spacing, column with spiral reinforcement definitely outperformed the one with the hoops. However, the spiral reinforced column and column with hoops with 1.5 inches of spacing performed pretty similar in terms of axial load capacity. So none of the columns experienced any transverse reinforcement yielding, which basically suggested that the confinement was not fully engaged. The average yielding of longitudinal bars was from 55 to 65%. And also, like, all of them basically yielded at the same time when we are talking about each column. And then the safety margins, basically, when we assess the design ACI design equation, we just propose that instead of using 0.65 for closely spaced hoops, we should use 0.75, the same value that we are using for the spiral reinforcement. And that would be all.
Okay.
Questions?
Thank you, Milana.